So welcome to day 9. I'm glad you're here. We're going to start off with a review. We're just going to bullet list the topics, the things that you definitely need to be able to do well on test 1. And then we're going to dive into chapter 4, which of course will not be on test 1. Okay. So let's kick this party off with an investigation just into the kind of list of things that you need to be able to do. Okay. All right. So list of topics, test 1 topics. I hear whispering. Let me just make sure that this is all the way off. Yeah, it is. That is off. Okay, great. Should be good. Well, let's just think back kind of to the beginning. We certainly need to be able to understand truth tables. What are the 2 kind of big main ways we use truth tables? I'm not talking about IO tables. I'm talking about truth tables. Let me take my glasses off so I don't have to. Anybody? It's a little bit better focus. Anybody? What did we use truth tables for? Like if you're wondering how to study for the test, you definitely want to be looking at your special homework, but you can also go back into WebAssign, even after you've finished your WebAssign, and look at those problems and the ones that you got wrong. You know, you can bring that stuff to office hours, or you can use the ebook. We used truth tables. Well, we used them first just to figure out how to evaluate like the and or not operators. That was the first time we saw them, right? When we built them for the P and Q, P or Q. But we're a little more sophisticated than that now. We're going to, the 2 main things that we have seen is you want to discover logical equivalences. You know, you want to know if 2 particular statements are logically equivalent. The logical equivalencies, you know, or inequivalencies. And a couple of things I noticed is sometimes folks don't answer the question. You might make the truth table, but then not answer the question. So you always want to address the question that's at hand when you do any problem. What else did we use truth tables for? Kind of the biggest, most complicated thing that we used truth tables for. Anybody?
Was it for that thing where like you would determine like a conclusion?
Determining argument validity, right? Is that what you mean?
Yeah.
Yeah, when we use that decision algorithm to figure out if an argument is valid or invalid. And there's a short video on that. Of course, the end of a particular lecture, we did that. So determining argument validity and invalidity. And again, you got to be sure and answer the question. I was surprised. Validity. Yeah, numerous people made a truth table, but there's some steps to that, folks, and you need to follow the steps. You make the truth table, make sure you've got a column for the premises and a column for the conclusion. Label them. Label the premise columns so you can get a look at which ones are the premise columns. That's all step 1. Step 2, you identify all the rows of interest. Those are the rows where the premises are all true. You need to know which rows they are, because those are the rows where you have to execute step 3. Step 3 is when you check the truth value of the conclusion. And then the decision is, hey, if the conclusion followed from true premises, in other words, if the conclusion was true in every row of interest, valid argument. If the conclusion failed in even one row of interest, invalid argument. Just, Hossein, where are you? Just FYI, folks. Chat GPT, can you make it so we can see it, please? We're not seeing you. We're seeing a football field with nobody in it. There you go. A Chat GPT is really no good at deciding if something is true or false. If you ask it to prove something that's a false statement, it'll try to give you a proof. So that's one thing it's not good at, and it's no good at determining argument validity, because it'll just give you kind of a line by line thing, as if the argument is valid in some rows and invalid in other rows. That's not the way argument validity works. An argument is either valid or invalid, period. One bad row makes the whole argument invalid. Then we played with circuits. And remember, there was kind of a threefold thing happening with circuits. Given a circuit, you should be able to construct the Boolean expression that is associated with it. But maybe, you know, you would be given the Boolean expression, in which case you'd like to be able to draw the circuit from that. Also, then there are I/O tables. By the way, folks, again, if you've gone to Chat GPT to look at I/O tables, you're doing yourself a great disservice, because they're set up incorrectly in Chat GPT. Under the input columns, the top of the column should always be starting with a 1, never with an O. And that's not the way that you would see it if you looked online for that answer. So we set up I/O tables the same way that we set up truth tables. The canonical setup is to start your variables like P, Q, R, input variable columns with a 1, like 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, under P, if it's an 8-row truth table, for example. You don't start them with O's. Same way we don't start a truth table with falses under the variables, whatever the statement variables are, P, Q, and R. You would never start a column under P, Q, or R with a false. You always start with true. And Chat does not know that. So I/O tables, if I give you an I/O table, you should be able to write the Boolean expression. And of course, from there, you should be able to get the circuit. So if I give you any one of these 3 things, you should be able to find the other 2. So the section on argument validity was section 2.3. Okay. Circuits and Boolean expression is section 2.4. We did do at the very beginning just a little bit with sets, element of, subset of, proper subset of, but I'll just kind of give you a big fat hint. Don't spend too much time studying the set stuff, because really the only reason we did that was so that we could have intelligent discussions using set notation later on, like when we looked at examples of multiply quantified statements. You know, we would use the element of notation, like for all X in the reals and for all Y in the reals, some property holds. So don't spend too much time on that, because if you understand how to read that something is an element of another set, that's really what you need to know for this test. You know, in the case that you get, you know, a problem where I give you an X that's an element of Z or something like that. Questions? Big topic, big important topic is conditional statements. We had a lot to say about if-then statements. It's a huge topic, and it's a very rich topic. We had numerous questions on homework using information about if-then statements. And there is that document in the good stuff folder called If P Then Q. If you haven't checked that thing out, I recommend that you do that. It's a great reference material that tells you everything you never wanted to know about if P then Q. The sister conditionals, how to negate if P then Q. Hey, does everybody in here know how to negate if P then Q? That's
P and
real
not Q.
important. P and not Q, exactly. Remember, and does everybody remember that every if-then statement is universally quantified? Yeah, and every universally quantified statement can be written as an if-then. So those are real important things to know. Of course, we have the sister conditionals like the inverse, the converse, the contrapositive, and this is really the only thing you have to memorize. I mean, maybe you feel like you have to memorize De Morgan's laws, but if you just think about De Morgan's laws for a minute, they make sense. But knowing the names of these, of course, is important. You also, I'll put negations in all capitals. You definitely got to be able to negate an if-then statement, right? So just for the note, the negation of if P then Q is P happened and Q did not follow, right? And then there was the biconditional. Hey, by the way, it wasn't on special homework, but I did assign problems from WebAssign that made you go and look at different ways to say P implies Q. Like there were a couple of problems. One was to figure out a way to write something is sufficient for something else as an if-then statement, or A is necessary for B. You had to be able to write that as an if-then statement, or A only if B. So review that if you struggled with those problems in WebAssign when you were working on those, all different ways to say if P then Q. Break out that if P then Q document in the Good Stuff folder and study that and go back and look at those WebAssign problems, because you will see stuff like that. So, there are many different ways to say if P then Q. You need to be familiar with those. Double check and make sure this is all. Okay. Then we had, in general, the idea of a formal statement versus an informal statement. Formal just means we're using symbols. Informal means we're using ordinary English, of course. De Morgan's laws for negating and or statements. You got to be able to distribute the not. So not P and Q and not P or Q. Be able to distribute the not across those two compound statements. And then that then led us into quantified statements and multiply quantified statements and their negations. Of course, you probably have had quite your fill of quantified statements after working those Tarski problems. And thank you for working so hard, on getting those done. I will get that graded and you'll get that back over the weekend so that you have that feedback before you sit for the test on Monday. Tarski, obviously, Tarski's gonna appear on the test, of course. Then the last thing that I'm thinking of is drawing a circuit to perform binary addition using adders and half adders. Half and full adders. There were numerous people who had not turned in that homework 3, and I sent out a call, asking people to go ahead and turn that in. I think one person did. I haven't checked in a day. I hope you did that homework. I didn't really get any feedback on why so many people did not turn in that homework. So it's, so I'm checking the chat again. If you emailed me today, like in the last few hours, I've been, teaching and commuting. So anyway, this is a good list if you feel comfortable with this, these topics, then you should do quite well. A lot of times, one of the questions we get, let's look at the gallery. One of the questions, that we get as instructors is, how many questions are going to be on the test? And, that question doesn't really make a lot of sense, because I could tell you 6 questions, but they could all take a really, really long time, right? Or I could say 20 questions, but they could all be short. I'll tell you what you're not going to see. You're not going to see a bunch of true false questions. It's going to be the kinds of questions that you have seen on special homework in terms of the way that they're presented. Mostly. I think I have one question where, you select all of the statements that are logically equivalent to something like that. But mostly it's, long answer. And the deal is, when a student says, how many questions are going to be on the test? What the student really wants to know is, am I going to be able to finish the test? Am I going to have enough time, to do it? And here's the deal. Yeah, you sure will, if you don't have to sit there and think for 10 minutes, before you start a problem. Like, if you sit down and you know what you're doing, you'll have plenty of time. But if you don't remember stuff, or if you don't feel confident and you're taking a really long time on some questions, it's just like anything, you might run the risk of running out of time. So what are good test taking strategies? Good test taking strategies. First thing you do, read over the entire test. Like, just take a gander, what questions are there. Put a star by the ones you know how to work, and work them first. Like, get a little confidence under your belt, right? Get the ones done that you're feeling great about. Then go back and start digging into the ones that you don't feel quite as comfortable with. And hopefully at the end of the test, you have time to check your work. What are you checking for? 1, did I answer the question? 2, did I follow the directions? 3, did I make a careless error, right? You're going to be checking for careless errors. But the first thing you want to check is, did I answer the question? Because you're sure not going to get full credit if you didn't answer the question. So, of course, I give generous partial credit. You've seen that from your homework that you get back. I try not to be brutal. And you won't have any kind of, like, maybe issues with accidentally writing down the wrong problem or anything like that, because the test will be right in front of you. You'll be able to write the solutions right on the test. There will be room. And for those of you who are on the TU main campus, I really look forward to seeing you in person for the very first time. And for those of you who are over at TUNE, I'm sorry I can't be in 2 places at one time, but somebody, either John Desmond or one of his associates, is going to be so kind to proctor the test for us there. So I wish I could see you all, but they can't. They said I can't make you come to the TU campus. I'm not allowed to make you come, right? But I'd sure like to meet you all in person. And I hope everybody does really well. We do have an office hour on Sunday night, of course. And if you're, desperate, and you want to email me for another office hour, like a Saturday or something, hey, you can ask. You can ask, what's the worst thing that happened? I might say I don't have time, but probably I would make time for you on Saturday afternoon or late Saturday morning. All right. Any questions? Well, let's get to our new material. This stuff is not on the test, of course, but I think you're going to enjoy it. I hope you do. I like this stuff. We're now in chapter 4. Okay. And this is not on test 1. I'll say it. I'll put it in writing so you don't have to worry about it. Okay. So listen, it's all about definitions. In fact, let me just talk to you for a minute. When we are trying to communicate with one another, whether that is through an email or, you're reading a book that somebody else wrote that they hope that you understand, or you've written some code and you want the person that's trying to use the code to understand the documentation that you put together for that code. If any of that kind of stuff is going on, what is really going on, I'd like you to think about it like this. When we read the written word, we are looking at sequences of symbols. Sequences of symbols. And the hope is that when different people are reading the same sequence of symbols, that in their minds, they are developing the same concept, the same idea about what that sequence of symbols represents. What ideas are being represented by a sequence of symbols. When you really think about it, it's kind of amazing. We're the only species that communicates abstract concepts and concrete concepts through sequences of symbols written down. So when we do want to write arguments that other people can evaluate and say, hey, that makes sense, that holds water, that's a valid argument, we need to be speaking the same language. And that means we have to have a shared dictionary of the meanings of words. It's particularly important in mathematics that we share the definitions so that everybody who's reading whatever it is that's being written agrees on the meanings of the terms. Super, super critical. So, to that end, I suggest that you might consider making a glossary, because we're going to have lots of definitions. We need definitions. So let's get started with our definitions. We're going to start simple, folks. We're going to start with the definitions of evens and odds. An integer x is even if x is equal to 2 times k for some integer k. There's a reason why I am formatting it like this. The point I want to emphasize is that definitions have more than one part usually. The first part of this definition is this equation that says, hey, x is even if x equals 2 times k. But notice, in introducing this equation, we have introduced a new variable, namely the variable k. And your reader would not know what k is supposed to be unless you told them, hey, that's an integer. For example, if all we wrote for this definition is x is even if x equals 2k, then somebody could just plug in pi for k and then they'd think 2 pi is an even number. It's not. Gotcha? So there are two parts to this particular definition, but the point I'm trying to make is in general, our definitions are going to have more than one part. What does that mean for us? It means when we are told something is even, then we will be writing down two things about that. It looks like 2k, but then k is an integer. The other thing is this: we might be asked to prove that a particular expression represents an even number. You see, definitions go two ways. You might know something is even, and then your job is to, prove something else, but that would hinge on the fact that this object that you were given is known to be even. That's using the direction sort of in the definition sort of in the forward direction. You know something's even, you have these two things that you get from that. But the other thing that could happen is you're trying to prove something is even. We still would have two things to deal with. We would have to prove the expression looks like 2 times some quantity, And then we would have to be able to prove that quantity, because it's probably not just a letter or a number, it's probably some expression with variables and numbers involved in it. We'd have to prove that that expression is an integer, you see? So that would be using the definition in the other direction. So definitions go two ways. And it's really important that we understand that definitions, if they have more than one part, all parts are important. An integer x is odd if x is equal to 2k plus 1, where k is in z. Now, I'm intentionally writing this part 2 of the definition of odd differently than I wrote part 1. Part 2 for this first definition. I just want you to see, hey, there's more than one way we can say that k is an integer. And you should be able to get comfortable with both of those ways of saying that. Another two-part definition. Anybody think of another way that you might have that we might have defined odd instead of x equals 2k plus 1? Can you think of another way we might have defined an odd number? No? All right, the point I'm making is we could have said x equals 2k minus 1. That would have worked. That would have worked. And the reason I'm talking about this is because I wanted you to know a curious fact about mathematics that you may not realize. Mathematics actually has etiquette. There is mathematics etiquette, and it's considered impolite to use a negative when a positive will do the same job. I just thought you might find that that's interesting, and it's true. So let's take a quick look at the evens and the odds, just to make sure that everybody's on the same page with what these represent, okay? The evens, if we use set notation, you could say dot, 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 -4, -2, 0, 2, 4, dot, 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 of course. And everybody sees enough of the pattern there to know what is to the left of the -4. Anybody? What would be to the left of -4?
-5. I mean, -6.
Yeah, -6. Good. So we're seeing the pattern here. You just write enough that you can see the pattern. And I'd like to just go ahead now and let's verify that, for example, -4 satisfies the definition of even. In other words, if -4 is really even, we should be able to write -4 equals 2 times some integer k. What would k have to be if we're trying to show -4 is even? Anybody?
-2.
Exactly. So -2 is clearly an integer. So that's that. Okay. By the way, remember 0 is neither positive nor negative. Remember that? 0 doesn't have a sign. It's not positive nor is it negative, but it does have parity. Parity, P-A-R-I-T-Y. That's the evenness or oddness of an integer. It has parity. And 0 is even. How can we prove 0 is even? Well, let's see. 0 would have to equal 2 times some integer k. What would k be, folks?
0.
Yep, nice. Good. So that's the evens. Let's take a peek at the odds just for completion's sake. In fact, you take a minute and see if you could write the definition of the odds sort of in a similar way that I have done for the evens here. But -3, you can go back to -5 if you want. You don't need to though. I think, you know, if you put a -5, cool, that's fine. But these are the odds, some of them, enough to see what's going on. So let's just verify. Let's go ahead. Let's verify that -1 really is an odd number. How do we do it? Well, we have to write -1 equals 2 times some integer plus 1. -1 equals 2 times some integer k plus 1. So what would k be here?
-1.
Yep. Right, you got to kind of overshoot the -1. You know, we go all the way back to -2, and then you come back to the right with a +1. And that's the game there. We can also prove that 1 is odd by writing 1 is equal to 2 times some integer k plus 1. What would k be here again?
-1.
Oh, we're looking at +1 now. 1 equals, if we put in -1, 2 times -1 plus 1 was -1. So we need to up k by 1.
0.
Yeah, 0 works. 1 is equal to 2 times 0 plus 1. Okay, so what's really going on with this, folks? The bottom line is when you divide an integer by 2, you got 2 choices of a remainder that you could obtain. If the integer x is even, when you divide it by 2, the remainder is 0, right? It's divisible by 2. 2 is a factor. If the integer is odd, when you divide it by 2, you get a remainder of 1. And we're going to come back to that idea of remainders when we divide integers by 2 or 3 or 4 or by any divisor d. And we're going to get into that a little more deeply as the semester goes on. Okay. All right, moving on. I'm just going to get a fresh piece of paper. We don't have a whole lot of notes tonight. We're going to try to discuss some things. So more definitions. We need 2 more definitions for this evening. Like I said, I want to just kind of sneak up on this idea of formal definitions so that you don't, feel completely overwhelmed with everything else that's on your mind. But these are kind of fun. Let's define prime and composite. Now, the definition of a prime number is different from the definition of an even or odd integer. And see if you can detect what's going on that makes this sort of different. An integer n greater than or equal to 2 is prime if its only positive divisors are 1 and itself. An integer n greater than or equal to 2 is prime if its only positive divisors are 1 and itself. Let me clean this up a little bit. Positive divisors. So the thing about this definition, folks, is it doesn't apply to integers that are smaller than 2. Like if an integer is smaller than 2, the question of is it prime doesn't even make any sense because that definition only applies to integers that are at least as large as 2. So when I was in grad school, one of the things that we used to joke about was, it's not the theorem that'll kill you, it's the definition. It was supposed to be a riff off that the thing that people say, it's not the fall that'll kill you, it's when you hit the ground. And the point of that joke was, it's not the theorem that'll kill you, it's the definition, is that, yeah, we're supposed to write new theorems, if you're trying to get a PhD in math, but if you don't have a decent definition, then you're not going to be able to get any theorems. The definitions are more important than the theorems, because without definitions, you can't write theorems because you don't have anything to talk about. And if you define things weirdly, or in a way that's not useful, you'll get no theorems anyway. So hey, notice first example 1. Notice 1 is not a prime. It's not prime because it's not bigger than or equal to 2. Because 1 is not greater than or equal to 2. And in fact, most of the theorems about prime numbers would fail if we allowed 1 to be prime. So my whole little story about, hey, the definitions matter, as much as the theorems. Case in point, if 1 was prime, a bunch of theorems about primes would fail flat. Okay. Example 2. The integer 2 is the smallest prime number. It is also the only even prime number. Further, it is the only prime that is even. Why is that? Why couldn't we have another prime number be even?
Because another prime number that, if it were even, it would be able to divide it by 2.
Yeah, exactly. A bigger even number than 2. If we tried to make that a prime, we couldn't, because 2 would be a factor that would be between 1 and n itself. Oh, I like to say, oh, you know what? I'm going to change this definition just by a little bit. I like to say an integer n greater than or equal to 2 is prime if its only positive divisors are 1 and n itself. It actually reads better if we say n itself. So 1 and n are the only positive divisors in itself. My bad. Okay, yeah, so that's our example 5, is this idea that no prime other than 2 is even, because any even integer n greater than 2 has 2 as a what we call proper factor, or proper divisor, i.e. a factor strictly between 1 and n. A factor that's not 1 and not n. It's strictly between 1 and n. So 6 can't be prime because 2 is a proper factor. It's not 1, it's not 6. So let's just go ahead now and make sure everybody in this room, kind of feels comfortable with the idea of a prime. Let's list the first few primes. Let's just make a short list. By the way, this course, the set of all primes is infinite. If that wasn't the case, then the RSA encryption code would be short-lived. It would be completely understood if it was a finite list of primes, because of course that encryption code hinges on very, very large numbers that have very, very, very large prime divisors. So of course, let's just do them in order. 2 is the first prime. What's the next prime? Help me build this list, folks.
3.
3. What's the next one?
5.
Thank you. Anybody else want to pitch in and help Edwin out?
7.
Thank you. Next one.
9. Oh, yeah. No, never mind.
That's okay. Keep going. You can find the one after.
11.
11, good. What's the next one?
13,
13, good. Keep going.
17,
17, nice. Next one.
19,
Yepper, keep going.
23.
3,
23, yeah, 23 is prime. I remember that birthday. I remember thinking, hey, 23 is prime. Keep going. Couple more. I know, like 24, no, 25, no, 26, no.
29,
29, yeah, 29. One more.
31.
That's right. And then we'll just do like this. Nicely done. By the way, have you ever heard of twin primes? Twin primes are prime numbers that are two apart. So like 3 and 5 are twins. 5 and 7 are twins. It's weird that 5 can be a twin with two different things. 11 and 13 are twins. 17 and 19. 21, 29 and 31 are twins. And there's hundreds of years old conjecture called the twin prime conjecture, and the conjecture is there are an infinite number of twin prime pairs, which is a little counterintuitive because if you start printing up the primes, they seem to get spaced further and further apart as the numbers get larger for obvious reasons, because there's more numbers that are smaller than them that can then become factors of those numbers in between, say making them not prime. And I don't know whether the twin prime conjecture was answered in the last couple of decades. I think it was Goldbach's conjecture that was answered in the affirmative within the last 15, 20 years or so. But I can't remember if the twin prime conjecture has been answered. If somebody wants to look that up and send me that for a little extra credit. The point is, there are still open questions, unanswered mathematical questions about, the primes for sure. They're not very well understood. Okay, so we've got this definition, and it applies to integers n that are greater than or equal to 2. So kind of in the same spirit that if you look at integers, just any integer, you can classify the integer as either even or not even, in which case, of course, it's odd. When we look at integers n that are greater than or equal to 2, we can classify them. Either they're prime or they're not prime, okay? Does anybody know the name of or the word that we use for not prime? You'd recognize it if you heard it. Composite. Does that sound familiar? Composite. A number that's not prime is composite. Okay. All right. So here we go. An integer n greater than or equal to 2 is composite if it is not prime. Composite if it's not prime. Perfectly true and perfectly useless. Perfectly useless definition. Let's think about why this is completely useless. It only tells us what a composite number is not. It doesn't clarify for us what a composite number is. Part of what is important in our definitions is that they yield equations. You see, when we defined even and odd, we got an equation, x equals 2k or x equals 2k plus 1, and we got information about the integer k. Listen, when you know a quantity is even, and you get this equation, and you get this information about k, it's like walking up to the math ATM and making a big cash withdrawal. It's like money in the bank, having an equation or an inequality or information like this that you then, you put in your math wallet, and then you pay that information out when you're trying to write a proof about an even quantity that's involved, in the statement you're trying to prove. Well, this kind of definition, it's like your count, is on 0. It doesn't help us at all. So it's not a helpful definition. So we need to try to understand how to say not prime. In other words, that the integer n has some positive divisors other than 1 and in itself. So to that end, here is the working definition of composite. It's the definition that we're actually going to use because it yields an equation and a couple of inequalities that we can actually do something with. An integer n greater than or equal to 2 is composite if there exist integers a and b such that n is equal to a times b, and 1 is less than a, and 1 is less than b. All kinds of proof money here, folks. You got all kinds of stuff going on with this. Okay, so here we go. We've got part 1, n equals a times b. That's an equation. Part 2, 1 is less than a. Part 3, 1 is less than b. And in fact, it's kind of embedded up here in the text, but this could be like the part 0, information about a and b. They're both integers. Okay, so just a quickie example of how we might, prove something is composite. Let's just do a real simple example. Notice n equals 12 is composite. Now there's a couple different ways we could factor 12 to get non-trivial factors, right? What do you want to use? There are a couple of ways to do it. We can't use 1 times 12, right? That doesn't help. But we need an a and a b that are factors that multiply together to make 12. Anybody want to suggest what we would use?
6 times 2.
Sure, 6 times 2. And of course, 1 is less than 2 and 1 is less than 6. These are both proper factors. And clearly they're integers. You almost don't even have to say that. You really don't even have to say they're integers. We know those are integers. Okay. Now, that's a super easy example because n equals 12 is just a number, right? And it could not be easier. By the way, this definition, if you look in the book, this is sort of a trimmed down version of what is normally given as the working definition. A lot of times what you see written is redundant. They say n equals a times b, and 1 is less than a is less than n, and 1 is less than b is less than n. But I claim we don't need to say that a and b are less than n because that is going to happen if both of them are bigger than 1. Let's think about it. I claim if we know that 1 is less than a, then that forces b to be less than n. Think about it. If 1 is less than a, that means a is bigger than 1, right? A is bigger than 1. Now, if b was as large as n, so if b was n, and we'd be multiplying it by something bigger than 1. How could n times a number that is larger than 1 equal n? See? So A being larger than 1 forces B to be less than N. See what I'm saying? So whereas in the book, you'll see 1 is less than A is less than N, and 1 is less than B is less than N. You don't need all that, because we're going to force A and B to both be less than N because they are both larger than 1. Questions? So this is our working definition of composite. We're going to see this again tonight. We're going to look at one more example that's not quite as straightforward. But before we do that, I'd like to talk to you about the things that we don't want to have to prove. Okay. All right. So there are certain things that honestly I would be hard pressed to prove if my life depended on it. Like right now, I'm not even kidding. Like stuff you learn in grad school and then you forget. Let me give you an example of something that you know, but maybe you just haven't thought of. Let's look at the gallery. Let's see people. All right. Let me ask you this. If you take an integer and you multiply it times another integer, do you believe that product is always an integer? In other words, does it make sense to you to say that the product of 2 integers is always an integer? Okay, I got a big old nod from Marcus.
Yeah.
Yeah, I mean, like, think of all of the, just think of a bunch of examples. Yeah, of course, the product of 2 integers is always an integer. That is a property that is true, and I would not be able to prove it if I had to. It actually hinges on a set of axioms called Peano's axioms. It's P-E-A-N-O, not P-I-A-N-O. Anyway, Peano was a logician. Anyway, the integers have properties, and one of them is if you take 2 integers and you multiply them together, you get an integer. Another property is addition, also has that kind of same thing going for it. If you take 2 integers and add them together, isn't the result always an integer? What about subtraction? If you take an integer and subtract it from another integer, is that difference always an integer?
Yeah.
Absolutely. So this essential property of the integers, where if you take 2 of them and add them, the result's an integer. If you take 2 of them and multiply them, the result is an integer. You take 2 of them and you subtract, the result is an integer. This property is called closure. And I want you to think about it like this. Think about the integer. You know how when we use set brackets, I was saying, hey, the set brackets are like the bag, and then the integers or whatever's in the sets are rattling around in the bag, and order doesn't really matter. Well, this idea of closure makes sense if you think about this bag. And if you take 2 integers inside the bag and you play the addition game, that result is still in the bag. The bag is still closed. Same with addition, subtraction, or multiplication. You take 2 integers, you play the subtraction or multiplication game, just like the addition game, that result is still in the bag, and the bag is still closed. However, if you take 2 integers and play the divides game, and divide one by the other, is the result always still in the bag? If you divide one integer by another integer, is that quotient always in the bag of integers? Is it always an integer?
No.
No. Can you give me an example that shows that that's, not a true statement?
1/2.
Yeah. If 1 is an integer, right, folks? 2 is an integer. 1 divided by 2 is 1/2. It's not an integer. So the 1/2 breaks open the bag. The bag isn't closed anymore because the 1/2 doesn't belong in there. It had to jump out. So that's the intuition behind the notion of closure. Okay. So we have things we may assume true without proof. Let me unpin me. Okay, things we may assume are true without proof. Sorry about the assume. And the first thing is this idea that sums, differences, and products of integers are integers. But we can say it differently. We can use this phrase closure. The set of integers which of course are denoted by a double bar Z, is closed under, and I'll put this in quotes, in parentheses, because a lot of times we don't say the operations of, we just say is closed under addition, subtraction, and multiplication. That's just another way of saying what I wrote up here. I will use both of these terminologies, and so you should familiarize yourself with both. They both are really talking about what we call the closure properties of Z. Sets are closed under various operations. Z is closed under differences, sums, and products. The reals are closed under sums, differences, and products. They're almost closed under division. If you throw away 0, then the reals are closed under division as well. There's another property that we need to be able to assume without proof. This is a property that you probably remember from high school when you perhaps had to factor a quadratic into like x plus 3 times x minus 2. Why did we ever do that? Usually because we were setting those factors equal to 0 to try to solve for x. We were looking for roots. We were looking where the graph would cross the x-axis. Remember that? Remember solving for roots of functions? Okay. If anybody ever wants to talk about roots of functions, I'll be happy to do that with you at another time. But the point is, here's the property that's involved. This is for any real numbers, not just integers. It includes integers, of course. For any real numbers, A and B, if AB is equal to 0, so if A times B is equal to 0, then A is equal to 0, or B is equal to 0. It's the inclusive or, so I don't need to say this, but I will, or both. This is called the zero product property. It makes perfect sense if you just think about it for a minute. I mean, we all kind of intuit what zero is all about. This is a basic property of the number 0. By the way, on a test or whatever, or even on homework, you're not going to be wanting to write out zero product property. We just call it the ZPP for short. But here is something that I want you to do later before we have our next lecture on Wednesday. So when you're looking over your notes, that's one thing that, I'll send out an announcement after the test and say, hey, we're going to be getting back at it on Wednesday. Please prepare by looking over the day 9 notes and be sure and do the due later. The due later is this. This is good review for test 1 right now. Write the contrapositive of the ZPP. Wouldn't kill you to do this tonight because it would be good review for the test or sometime before test 1. Because remember, folks, this is an if-then Of course, any universally quantified statement is an if-then. We learned that, right? The contrapositive is another if-then. It's also universally quantified. So the contrapositive would start just like this does. It would start off for any real numbers, A and B, but then of course, instead of if P then Q, it would be if not Q, then not P. Recall, why am I asking you to write the contrapositive for crying out loud? Well, it's not random. Recall, the contrapositive is logically equivalent to the original. Remember that? Those are the two that are logically equivalent to one another. That's why the converse and the inverse are logically equivalent. They are contrapositions of one another. And I have just lost my camera. My phone is shutting down. So sorry, you're not going to see my face for the next couple of minutes, but I'm sure you'll live without it. Let's just go through one more example, but let me just finish my thought. Why am I asking you to write the contrapositive? Because that's the formulation of this that we're actually going to wind up using. We're actually going to be more often than not using the contraposition of the zero product property when we're trying to, use the zero product property. Okay, let's do one more example. And it's going to be about composite numbers. So I'm going to put the definition of composite back up here. We're also going to use closure properties. Okay, sums, differences, and products of integers or integers. And we're going to prove something is composite, something a little more complicated than 12. And that is how we will wrap up tonight. For X and Y in Z, so we're looking at two integers, where X is greater than 1 and Y is greater than 1. Consider this expression. Okay, the expression is N equals X squared Y minus X. X squared Y minus X is in a composite number. See what I mean? It's not just going to be like X is 12, N is 12, it's going to be more interesting than that. Is in a composite number. What do you think, folks? Here's our working definition of composite. Can we write N? Well, first of all, do we know N is greater than or equal to 2? Do we even know that? Let's just assume it is and see if we can at least factor it. Can we factor in as A times B, where we'll be able to show that both A and B are bigger than 1? What do you think? Anybody got any opinion? Made it look worse. Oh well. Any opinion? You know, I can only see the top of your head, Eric, barely. Brianna, I cannot see you at all. Hussein, where'd you go? Ahmed, where have you been? Marcus, top. Is it because y'all are using laptops? Is that the deal? Is that why I can't see you? I wish you'd adjust your setup so that, you know, you could be seen. All right, anybody got any ideas? We got 5 minutes. We're going to use it. Thank you, Ahmed.
I'll just guess no.
Your
That
guess
is
is no.
composite.
Okay. Well, at least you guessed. That's fine. Thank you for, you know, saying something at least. All right, so the point of this exercise is that I'm going to demonstrate how we actually verify that the different parts of the definition of composite are satisfied. This actually is composite. Let me show you why. I'd much rather somebody try and, you know, not be right than nobody say anything at all. Okay, so listen, we're going to factor it. We're going to factor x out of both of those terms, leaving xy minus 1 as the other factor. Okay. X is going to be our A, and xy minus 1 is going to be our B. All right. Now, so we've got it factored. We're going to have to discuss why A and B are both integers, and we're going to have to discuss why they're both larger than 1. Let's start with the inequality part. Well, notice also A, which is equal to X, okay, is greater than 1 is given. We were told X and Y are both greater than 1, okay? So if A is X, so I could say let A equal X and B equal XY minus 1. We should probably write that, okay? So X is bigger than 1. Now, what about B? B is X times Y minus 1. But we know X and Y are both bigger than 1, right? We're told that. They're integers. So what is the smallest that XY could possibly be?
4.
4. So this is greater than or equal to 4 minus 1. Because X and Y are greater than 1. So B has to be bigger than or equal to 3, right? Because at worst, it's 4 minus 1, you know, but it could be much larger than that. So B is greater than 1. So A is greater than 1 because it's equal to the X, and B is greater than 1. Now we have to verify that these are both integers. And that's where we're going to use this closure property of Z. Sums, differences, and products of integers are integers. Okay, that's the closure property. Sums, differences, and products of integers are integers. All right, so let's check it out. Well, listen, we're told A is X and X is an integer. So we know A equal X is in Z because that is given. You know, X element of Z is given. We were told that. All right. But now we got to deal with B. Now, B equals XY minus 1. Well, hey, let's think about it. How is B being built? Let's think about it. The pieces are X, Y, and 1, where X, Y, and 1 are integers, right? We know those are all integers. So X and Y are integers. Well, that means the product XY is an integer, right? Because products of integers are integers. So XY is an integer, 1 is an integer, XY minus 1 is an integer because differences of integers are integers. So we just have to write that down. We just have to say it. And there are, you know, easier or harder ways to say it, but you can just say since Z is closed, under multiplication and subtraction, I like to write the one that happens first, but you don't have to. B is an element of Z. So in fact, let's just recap. N is equal to A times B, where we proved 1 is less than A, right? A bigger than 1 means 1 is less than A. B was bigger than 1, so 1 is less than B. And A and B are in Z. That's what it takes to satisfy all the parts of the definition of composite. When it's not n equals 12. When it's actually kind of something a little more interesting. So this is a sneak preview. This is just sort of a beginning. We're going to be dealing with definitions. We're going to be satisfying definitions. We're going to be, using all the good stuff that definitions give us in order to prove statements. A lot of what we're going to prove this semester. I'm going to just put the camera back up and put us back in gallery. A lot of what we're going to prove this semester is going to seem maybe even silly. It might even, you get to see my kitchen. Oh no, kind of silly. Like we'll start with things like prove that the sum of any two even integers is an even integer, or prove that the difference of two odd integers is even. Like we'll start with silly stuff, but eventually we're going to start to do some interesting stuff. And in fact, by the end of this semester, you will be able to prove and really understand why the set of all prime numbers is infinite. We're going to prove that. You're going to prove the set of prime numbers is infinite. We've got some really interesting things we're going to prove eventually. But in order to, we got to work up to being able to do that. Another thing you're going to learn to prove, that you're going to be able to prove by the end of the semester, is that the square root of 2 is irrational. Like you're going to totally understand it. It's going to make sense. So things to look forward to. We got to start with the baby stuff, but there are cool things for us to learn and to prove. And I hope you're excited about it, because everything that we just did, all this logic stuff, all this if P then Q stuff, that's like the bones. That's the skeleton that we hang, the meat, the ligaments, the muscles, the skin, to make a real mathematical, homunculus, for lack of a better word. Like I'm just saying, it seemed really dry, right? Chapter 2, even chapter 3, even with Tarski, right? It seems dry, but there's a reason why we did all that, because we need to understand what it takes to make a logical argument before we can make real logical arguments about interesting things. And that's what we're getting ready to dive into now. We're going to learn some interesting stuff. All right, so I'm going to stick around. I'm going to stop recording, but I'm going to stick around in case anybody wants to chat or has any issues. I've got a few minutes before I have to give an office hour. And today's Wednesday, right? So office hour at 8 o'clock if you want to come into the office hour. But I'm going to stick around. I'm going to stop recording.